Greetings. Today we're going to learn about extreme values. This first question is a warm-up question from Calc 1, so I fully expect you to be able to do it. Here we have a function, and we're trying to find the local and global min and max. So usually we take the derivative. Derivative is 3x squared minus 3. Alright, so the derivative gives us slope. If the slope is 0, then we have a critical point. So critical points, we get it by setting the derivative equal to 0. So that means x squared is equal to 1. So x equals plus or minus 1. Those are our critical points. But also we have boundary points. Those are critical points as well. So -2 and 3. So we can evaluate this function at these points. Let me do them in order. So let's evaluate it at these points. So f of -2 is -2. F of -1 is 2. 1 is -2. 3 is 18. Alright, so immediately we see that for global, your textbook calls them absolute. I like the word global. Global max here, 18. And then we have global min at 2 places, and that's okay. They're co-minimal, so we're not stingy. They can both be considered minimal. What about the other one? It's not a global min or max because it's in between those two. So you can use the first derivative test or second derivative test to see if that's a min or max. I personally like to use the second derivative test. So that's this thing. F double prime at -1 is -6. Yeah, so that means it's concave down, and so that one, the one that we don't know, is a local max. I can briefly graph this. You should probably graph this on Mathematica, but it looks something like this. Yeah, so this is 18 there. These 2 points are the co-minimal points, and then this is the local max. Yeah, alright. So having done this exercise with with single variable calculus, you can use the same idea to think about multi-variable version. F has a local max. Over here, the local max, it's bigger than everything else around it, but maybe not for things that are very far away. So we need to say that f of x comma y is less than or equal to f of a comma b. As long as x comma y is near a comma b, for all x comma y near a comma b. Yeah, that's it. Let me draw a picture. So locally, we have some surface, and then if you draw a tangent plane there, everything is lower than that. And so if you look at, so critical points are points where we need to examine. And so if we look at this one, it means that both the x derivative and the y derivative, both of them are flat. So it's a critical point in the x direction, it's a critical point in the y direction as well. So then we can write that so f sub x is equal to 0, the partial derivative with respect to 0, x is 0, or f sub x ab is undefined, does not exist. So this means that it's potentially a critical point in the x direction. And if it is not going to be a critical point in the x direction, that means on one side it might be bigger, the other side is smaller, then that's not going to be a max in our case. In our case, it is a max in the x direction. It's also a max or min in the y direction, so we have the same condition. And then we want both of these or either of them. So let's think for a moment. If we have a picture like this, the tangent line in the x direction, that's this one, is flat, and in the y direction it's also flat. We want both of them to be critical points, so we want both. That's our definition for a critical point. Okay. So then we have a theorem, and this is a really nice theorem. It's directly the same as the single variable case. If we have a local extremum, namely a local min or a local max, then the point is a critical point. It doesn't go backwards. Yeah, we could have critical points that are not local min or max. We could have things that are just very flat, like this is y equals, you can't see this, y equals x cubed. Remember, that's our prototypical case where we have a first derivative. The tangent line is flat, but it's not a critical point because it sort of plateaus there and then keeps going. So it's, it is a critical point, but it's not a local min or max because on one side is smaller and the other side is bigger. So we don't know that all critical points are local extrema, but all local extrema are critical points, and so that's the direction we need. Yeah. So if we're looking for local extrema, we can just examine critical points. Some of them are going to turn out to be local min, some of them are going to turn out to be local max, and some might be neither, and that's fine. So here is an exercise where we find the critical points. So I'm just guiding you to find the critical points first. Now, the critical point says that, well, 0 is equal to f sub x, the x derivative. What is the x derivative? That's 3x squared minus y. And let me write out the other condition as well, then we'll work on them one at a time. So we also should have the y derivative be 0. The y derivative, I'll write them symmetrically, so 3y squared minus x. Okay. So then, if we go back to look at the first one says that y is equal to 3x squared. The second one says that x is equal to 3y squared. If we put those two things together, we get that x is equal to 27 x to the fourth. To solve this, be very careful. We should move everything to the same side and factor. So 27x to the fourth minus x is equal to 0. And if we factor, we get x times 27x cubed minus 1 equals 0. So then either x is 0 or 27x cubed minus 1 is equal to 1. So that means x is equal to a third. Okay. So those are our two cases. Notice up here, you might have been tempted to divide by x. If you divide by x up here, then you would have lost the solution x equals 0. Okay. So let me write out the critical points. We have 0, comma, if x is 0, then y is 0. So that's a critical point. The other one is a third. So if x is a third, then y is also a third. So those are our critical points. How do we classify whether they're local min, max, or neither? Earlier up here, we just graphed it, and you can just see that which ones are min or max. Or you can use the first derivative test, or you can, first derivative test, I didn't do it, or I used the second derivative test up here. So we'll have these three tests. Yeah, graphing it, that's just a quick way to see it. Or we can use the first derivative test, or we can use the second derivative test. and so they have correspondences to our multivariable situation. Alright, so now we're on the backside of the worksheet. Critical point that's not a local extrema is called a saddle point. If you don't know what a saddle looks like, you can Google it. It's what you use to ride a horse. Right? So just anything that's not a local max or local min, if it's a critical point and turns out to be not a local extremum, then we call it a saddle point. Doesn't actually look like a saddle all the time. And the methods I already mentioned on the previous page, we can graph it and eyeball it. I have some Mathematica demo that you can run and try it with this same example from last page. Okay, so run that now. Just make sure you have done that. Plot a contour map, and you can see that as well. Contour map, if it's a min or a max, it looks like concentric rings, and it gets either bigger and bigger or slower or smaller and smaller in the middle, depending on the shading of the color. So then you can tell that it's a min or a max if you can see the colors. A saddle would look like something like this, an X, and then things will look like this. So then if you go, for instance, to the left and right, it increases, and then if you go top or bottom, it decreases, for example, right? Then that looks like a saddle. It's neither min or max because you can move in some directions and get bigger, or move in some direction and get smaller. And finally, the third test is the second derivative test, and this one requires more, calculations. So I'll show you. So the second derivative test, this one is the conclusion. This theorem is in your book. Yeah, I'm not gonna spend time writing this out. You really should have looked at your book and then copied down this theorem, right? So I expect you to be at least able to do that. Right? So now I'm going to show you how to use the second derivative test. The second derivative test involves calculating second derivatives. So let's do that. So f sub x, what was f sub x? I had it on the previous page. So let's see. Where is this? 3x squared minus y and 3y squared minus x. Let me copy that over. So f sub x was 3x squared minus y, and f sub y was 3y squared minus x. So I'm continuing with the example from the previous page. Then I need second derivatives. F sub x. Here I'm taking the derivative of this thing, so that's 6x, because y is a constant, so that goes away. If I take the derivative with respect to y, then it will be negative 1. Similarly here, if I take the derivative with respect to x, it's negative 1. These two are always the same if our function is nice. We had this theorem before, Fubini's theorem. You don't actually have to take both of them, but it's a good way to check, I think. So why not? And then take the derivative with respect to y, that's 6y. So now I can write out d. Let me write d of x comma y. This is f sub xx, f sub yy, minus f sub xy squared. So that's equal to 6x times 6y minus negative 1 quantity squared. So that's 36xy minus 1. And now we can plug in d equals 0, 0. Sorry, d of 0, 0. That's negative 1. And because that's less than 0, that means 0, 0 is a saddle point. Saddle point. And then let's calculate d of a third. Remember, these are our two critical points, 0, 0, and a third from the previous page. If we plug that in, 9, 4, 4 minus 1 is 3, 3 greater than 0. So then that means we have a local min or max. Right? So that means local extrema. and then I could look at the second derivative. Just pick one direction. Maybe in the x direction. I could use the y direction as well. I picked this one, and that's 2. 2 is greater than 0, so that means it's concave up in the x direction, so it has to be a local min. 1/3, 1/3 is a local min. So your intuition is that, if f sub xx and f sub yy are different of opposite signs. For instance, if this one is positive and that one is negative, then it means in the x direction it's concave up. I don't know which one I said, but anyway, one of them is concave up, the other one is concave down. So then that looks like something like this. One direction concave up, the other direction concave down, and that looks like a saddle. I don't know how to draw it, but imagine it's a saddle. Okay. So then that's a saddle. So if f sub xx and f sub yy have different signs, then when we multiply them, we have a different sign. And if we have a negative thing and then we subtract something, it will still be negative. So that shows that if we have different signs, we'll end up, so we have a saddle like that, we have different signs, we'll end up having a negative number. And so that's our conclusion. If they are of the same sign, then we multiply them together as positive. Because they're both positive or both negative, we multiply them together as positive. Okay? So we hope that means it's a local minimum max. But of course, there are other saddles that look ridiculous. If f sub xy is really, really big, that means then this term is going to be negative, really, really large, and it could overpower this term and could still turn into a saddle. That's the case that's harder to imagine. So then you just have to take this theorem by faith. That I'm telling you that that's a true statement. It's beyond the scope of this course to prove this theorem, so we're going to be using it. But at least you can understand one half of the theorem, why the saddle point case is that case. All right, so that's it for today. We have a sort of a shorter worksheet, and the next worksheet is super short. All right, so to give you a time to rest a bit. All right, that's it for today. Bye.